How did life begin? It's one of the most fundamental and difficult questions, and has challenged us for eons. For years, scientists have been investigating this extraordinary puzzle, trying to figure out how non-living matter could have come together to form a living thing. It's a quest that drives scientists to look for clues at the very ends of the Earth, and even deep into space, searching for the secret of life. Our planet teems with life. From the highest mountain to the deepest ocean, life is everywhere. But how did it begin? How did life emerge on what was once a lifeless planet?
And I think it's just one of those big questions. I mean, people like to know where they're from and how they got there.
Science now hopes to be able to answer this age-old question. Huge strides have been made, and extraordinary theories are now being investigated by some of the world's leading scientists. Some propose that life emerged from a warm volcanic pool. Some suggest it began deep on the ocean floor. And others believe that it developed out in the blackness of space.
This is the time to be alive and working on this field of origin of life, because we now have the confidence that there are scientific ways of tackling the problem, but there's still so many unanswered questions.
We want to know what's on our planet. We want to know what's out there in the universe. We can't help but be fascinated by it.
A first step to understand how life began is to try to figure out where it began. For generations, it was assumed that life began on the Earth. Then, in 1903, the Swedish chemist Svante Arrhenius came up with an outlandish idea: panspermia. His theory is that life was created in space or on another planet, and the seeds of life dispersed out into new worlds. NASA scientist Scott Sanford investigates the possibility that life may have started in space.
Panspermia is not totally impossible. We know samples of Mars have made it to the Earth. So if you had life on Mars, maybe it could have been delivered to us in that way. But even if panspermia did explain life getting started on the Earth, it doesn't explain how life got started in the first place.
Sanford is not convinced that life itself was delivered to the planet, but he does believe that some of the starting materials, the building blocks of life, came from outer space. And their delivery system was a comet.
Comets are delivering building blocks. They're not delivering living systems. They're delivering the components from which you might be able to make living systems.
Comets are made up mainly of water and dust, with traces of carbon dioxide, methanol, and ammonia, all frozen into a giant, dirty snowball. Sanford believes that they also contain small numbers of organic compounds, some of the building blocks of life. But there's a problem. How did they get there? These building blocks are almost always put together by living things. They are complex carbon-based molecules like proteins, carbohydrates, and nucleic acids. So how did building blocks end up on a comet? Unlocking this riddle is the first step to understanding this theory of the origin of life. Sanford suspects that the unusual conditions on comets might lead to the formation of these organic molecules. So he sets up an experiment to test his idea. His first task is to recreate temperature conditions found in space where the comets roam. He has to achieve temperatures approaching -450 degrees Fahrenheit. To get an idea just how cold that is, look at what happens to air when it is cooled to below -300 degrees Fahrenheit.
That's liquid air, basically. And you can demonstrate this by taking, let's say, a balloon, which is simply air in a container.
When Sanford places the balloon in the liquid nitrogen, the air inside it cools, and some of the gases turn into liquid.
And then when I remove it, so you can see the balloon is flat, but as it warms up, it will return into a gas and blow the balloon back up. This only happens because the liquid nitrogen is at a very low temperature. So if we were to put this nitrogen in the machine back there, it would turn into a solid. So in fact, this liquid nitrogen, as cold as it is positively tropical compared to the kind of temperatures we normally work at when we're doing these simulation experiments. Whoops, we popped it.
Sanford introduces substances found on comets, such as ammonia, carbon dioxide, and methanol, into his comet simulator. They instantly freeze. The sample is then bombarded with radiation from a hydrogen lamp. This simulates what happens when the comet receives radiation, for example, cosmic rays and gamma rays, and then passes close to the sun. Radiation and heat can transform the simple molecules into an array of organic compounds, ranging from proteins to amino acids. And Sanford uncovers the secret of how this transformation occurs. Some comets pass around our sun in highly elliptical orbits. When they are far from the sun, the molecules that have been irradiated are tightly locked in place, frozen into a solid chunk of ice. But when they get closer to the sun, things warm up and the molecules get a chance to make their move and react.
If you start to warm that ice up so that things can move a little, then they start to find each other and they react. But they don't react with their preferred partner, the person who would make them the most stable. They react with whoever they're next to. So you have these marriages of convenience. And as a result, the chemistry is not the kind of chemistry you think of in your freshman chemistry laboratory.
Sanford shows how the building blocks of life can be created on a comet. But how do they get down to the surface of the Earth?
A comet can deliver material to the surface of a planet in several ways. Of course, the whole comet could run into the planet, but that's a rather destructive way to do it. But more elegantly is to have the comet shed dust, as we see in a comet's tail, and that dust can then hit the planet's upper atmosphere, slow down without burning up, and then settle down to the surface. We have comet dust raining down on us all the time, even now.
It's an incredible theory that comets can rain down the chemistry set needed to start life. So in February of 1999, NASA launches a bold mission to intercept a comet and return with a sample. It's a chance to test Sanford's theory.
Was recovered nicely from liftoff transients.
After 5 years of flight, the probe, codenamed Stardust, arrives at its target, just behind a comet known as Wild 2. Dust particles from the comet's tail stream into a honeycomb collector filled with a specially designed aerogel. When scientists at NASA analyze the dust, they discover a vast array of complex organic chemicals, including aminos and hydrocarbons. This confirms Sanford's theory that comets contain building blocks of life.
When you want to make life on a planet, you don't necessarily have to start from scratch on that planet, but that delivered to the planet from outer space may be compounds that can play important roles in getting everything going.
It's amazing to think that life could have been kick-started using organic building blocks delivered from space. But one British scientist thinks that life itself was created on board a comet. Does that mean we are all descended from an alien life form? The search to find out how and where life began has puzzled scientists for generations. Chandra Wikram Singha, professor of astronomy at the University of Cardiff, agrees that comets had a role in the birth of life, but he believes that life itself began on a comet.
comets are the best places for life to originate. Our planetary system is surrounded by 100 billion comets. So you are multiplying the odds in favor of life starting on any one of those comets over that on the Earth by a huge factor.
Wickramasinghe proposes that the organic molecules found inside comets came together to make the first single-celled life forms. It's a bold and controversial theory.
At the beginning, we were regarded as heretics, would have been perhaps burnt at the stake if we lived in medieval times. We were certainly mavericks, there's no question about it.
Wickramasinghe's radical claim is that cold, icy comets not only contain complex organic compounds, but also the other essential ingredient for starting life: liquid water. The water forms when radioactive isotopes decay, giving off heat, melting the ice at the center of the comet.
Think of this as our dirty snowball comet, hard frozen on the outside, temperature minus 300 degrees Fahrenheit. The radioactive elements in the comet will be heating it up from the center, and this is what I'm going to simulate by putting it in a microwave. These are radioactive elements that are in the middle of the comet, and they release energy that begins to heat the comet from the inside. And let's see what's happened now with the inside heated by radioactive heat sources in the comet, and in this case we find the interior all melted and gooey, and the outside, the crust, is still intact and frozen and cold. The gooey liquid interior of the comet, which was heated by radioactive heat sources, it's chock-a-block with organic building blocks of life and a lot of liquid water as well. I think life originated in this gooey pool in the middle of a comet.
In 2005, NASA engineers choose the comet Tempel 1 for a daring mission. They plan to smash a probe into the comet, exposing the inner core. The results of the mission could prove Wickramasinghe's theory. This mission will test the engineers' abilities to the limit. The 820-pound payload will have to travel across space to intercept a comet traveling at 10 times the speed of a bullet. After 6 years of meticulous planning, finally on January 12, 2005, the Delta rocket carrying the Deep Impact Probe launches into space. After a 268,000-mile journey, the impactor, about the size of a school desk, separates from the mothership and hurtles toward the comet. It scores a direct hit. These images from space and Earth-based telescopes show the moment of impact. For the first time, the secrets of what lies inside a comet are exposed. From a lofty perch in space, the Spitzer Infrared Space Telescope analyzes the unique signals given off by the compounds contained in the plume of comet dust. An amazing array of ice and fine dust particles are seen. But to everyone's surprise, the data also shows that the comet contains clay, the same kind of clay that can be found on Earth. And it's thought the only way to make clay is with liquid water. Wickramasinghe believes that this is proof that at some point in time, Tempel 1 did have a gooey liquid water interior. With liquid water and organic molecules, comets could be incubators for life. Comets like Tempel 1 could be packed with microorganisms ready to seed life throughout the galaxy.
We here on the Earth are connected to a much, much bigger cosmos. Life on the Earth is part of a connected chain of being that extends to the remotest corners of the galaxy, maybe to the remotest corners of the universe. We have our cousins out there.
But whether life began inside a comet or on the Earth, what is still completely unknown is how it happened. How non-living organic molecules combined to create the first living thing. This Big Birth is one of the big unanswered questions in science. The ancients used to believe that life could emerge spontaneously. A frog could emerge from stagnant water, or flies from rotten food. In the 19th century, Charles Darwin proposed that perhaps life emerged only once, many millions of years ago. He suggested that this Big Birth then led to all life today through a process of evolution. Starting with the simplest possible life form, more and more complex creatures evolve. As each new species emerges, it forms a new branch on the tree of life, and working backward in time, we can see our ancestors. Scientists propose that all life on Earth is descended from a single microscopic organism, what's known as the last common ancestor. Understanding this ancient microorganism will help scientists uncover the secrets of the Big Birth. The quest to understand the birth of life has sent scientists looking for clues around the world and out to the far reaches of the universe. They want to understand the moment when inert chemicals came together to produce the first living thing. One approach is to unravel 4 billion years of evolution, to travel back in time to uncover the oldest and simplest forms of life. And the Holy Grail is a theoretical 4 billion-year-old microorganism known as the last common ancestor. This tiny cell gave rise to all life on the planet, and close relatives may still be alive today. There are estimated to be 3 billion separate species of microorganism on Earth, but less than 1% has so far been discovered. Hunting them down is NASA biologist Dr. Lynn Rothschild.
All you have to do is look under a microscope, and they are so incredibly cool. When I was 8 years old, I looked through a microscope and I just fell in love. I realized that they are absolutely at a crucial step to study evolution. And so that's the direction I went with my own research. So I get to have fun and get to study something important.
Rothschild is traveling 14,000 feet above sea level to the Altiplano in southern Bolivia. It's a hostile landscape where temperatures regularly drop to -4 degrees Fahrenheit. It also has some of the highest recorded levels of ultraviolet radiation on Earth. But it could be the perfect place to find a close relation of the microbe that gave rise to all life on Earth, the last common ancestor.
Coming up into the Bolivian Andes here seems like the last place on Earth we'd go to look for early life. But we found organisms up here that are probably like the earliest organisms on Earth. Hey, maybe we're even going to find ones that are similar to the last common ancestor of all of us.
Rothschild scours the Earth, looking for microbes living in extreme conditions. It turns out that these microorganisms, called extremophiles, may be closely related to the most ancient forms of life.
You have to really go to unusual environments to find ecosystems that are just microbial. I hope that those organisms prove to be extremely deep branching. In other words, organisms that seem to be much closer to our last common ancestor than you or me.
Next stop for Rothschild is a landscape of boiling mud. Superheated steam, warmed by shallow bodies of magma, shoots out of the ground. Hot geysers like this would have been present on early Earth, so Rothschild hopes to find life in these extreme conditions.
The earliest common life form that we're all descended from lived in very high temperatures.
Rothschild works meticulously, logging the exact temperature and position of each sample she takes. A great challenge for scientists trying to understand how life began is that even the most basic microorganisms alive today are still incredibly complex. When looked at on a microscopic scale, the intricate complexity of a cell is clear. From its ability to reproduce to the way it converts energy, every process in the cell is carried out by an extraordinary interplay of complex organic molecules. But the ancient microorganisms that Rothschild is tracking down in Bolivia could give us clues to the nature of the first organisms. As the sun dips below the horizon, the temperature plummets. Rothschild takes refuge from the harsh environment where these modern cousins thrive. Overnight, the temperature drops well below zero. Next morning, the vehicle won't start. Dr. Rothschild also feels the effects of the thin air 14,000 feet above sea level.
It's not much fun for us when we drop our oxygen levels just a few percent, but on the early Earth there was no free oxygen whatsoever. So just to time travel back just a little bit is a huge price to pay for us humans.
Rothschild's next hunting ground is the Laguna Colorada. Its red color gives a clue about the very unusual type of microbe she hopes to find. This part of Bolivia boasts one of the highest UV counts of anywhere in the world. The thin atmosphere at this high altitude only partially blocks the sun's radiation, making living conditions here closer to those of the Earth 4 billion years ago.
When life first arose, the level was incredibly high, vastly higher than we see today. And so by coming up here, even though we're not able to simulate the early Earth, because of course we couldn't live under those conditions, at least we can time travel a step backwards and get some idea what it would have been like for organisms in the past.
Dr. Rothschild measures the levels of UV radiation.
These readings are amazing. I mean, this is the middle of winter and already we've got extremely high UV readings, and I bet they're going to be even higher by noon. It's just amazing.
Readings here can reach twice the average level of a California beach. And just as our skin is in danger from too much UV when we lie in the sun, the microbes that live here in Bolivia are at constant risk. Rothschild carries out a simple experiment to find out just what they are up against.
What I'm doing now is looking at the effect of ultraviolet radiation from the sun on naked DNA.
The naked DNA is a solution containing DNA molecules stripped of any protection from the cell that would normally surround it.
And then what I'm going to do is seal it up and leave it out in the sun for a few hours.
After just 2 hours of UV bombardment, the DNA molecules show severe damage. Levels of UV on the early Earth would have been around 100 times higher. Many scientists think that our last common ancestor had to live in the dark depths of the ocean or buried under the ground for protection. But the microbes here managed to survive. Their red pigment helps protect their DNA.
Just like we suntan in the summer to protect ourselves, these organisms produce red pigment.
But even though we know that UV radiation is very damaging to the DNA in all living organisms, there's also a flip side. UV radiation may have helped to drive evolution. It might even have had a role in kickstarting the Big Birth and the evolution of the last common ancestor.
Ultraviolet radiation produces mutations. Now, mutations aren't all bad. Without mutations, we wouldn't have evolution. You need to have change in the genetic material to have change in the organisms. And our world, of course, would be very different if nothing had ever changed. We wouldn't be here.
Dr. Rothschild's study of these microbes will help scientists understand how the first organisms survived the hostile conditions on the early Earth, and give a clearer picture of what our last common ancestor was like. But another great mystery remains. How did the last common ancestor form? What is the link between the building blocks of life and the Big Birth? It turns out that some of the answers to that great puzzle may emerge from an extraordinary place in the depths of the ocean. The question of how life began has troubled scientists for centuries. Darwin's theory of evolution explains how species evolved, but we still do not understand how the first living thing was created, how evolution began. Creating life had been the stuff of science fiction.
It's alive! It's alive!
Then in 1953, a bold experiment began the modern scientific investigation into the origin of life. Stanley Miller tries to recreate the conditions of early Earth when scientists think life began. John Chalmers was an associate of Miller and now works in his lab.
Stanley's was the first one to really have a research program directed towards the origin of life. It changed the ideas about the origin of life from mere speculation to a research program.
Since Darwin's time, a lot has been learned about what the planet was like 4 billion years ago. It was an extraordinarily violent time. The Earth had only just formed and was continually bombarded by meteors, asteroids, and comets. And the atmosphere was very different to what we're used to today. Stanley Miller's experiment recreates these conditions in the lab. The flasks contain what Miller believed were the key components of the Earth's early atmosphere: methane, ammonia, and hydrogen. The warm water represents the early ocean. But the key component was a Frankenstein-like bolt of lightning, a simulation of the electric storms that would have raged on the young planet. Miller started the experiment, and the next day, when he returned to the lab, he was in for a shock. The liquid in one of the jars had changed color, and when he analyzed the substance, he found something remarkable. It was packed with chemicals called amino acids, what biologists and chemists call the building blocks of life.
Of course, they're very important because all terrestrial life is made up of amino acids.
Miller's experiment showed how simple molecules could be transformed into the building blocks of life. But these building blocks are still a long way from any kind of life. How do these so-called building blocks create life? One clue was to come from a very special package that was delivered to the Earth from space. In September 1969, the residents of Murchison in southern Australia were startled by a loud bang. A 200-pound meteorite fell into their village, showering it with rock. These small pieces of space rock have been the object of intense study ever since. Dave Deemer at the University of California, Santa Cruz managed to get his hands on a sample.
There was a flash of light in the sky and a rolling thunder, and a few minutes later, the stones of the meteorite just fell all over Murchison, Australia, and there's a strange aroma in the air.
Deemer extracts a compound from his small piece of the meteorite, which has the same aroma.
So when I'm smelling this, I'm smelling an aroma that's 4.57 billion years old. That's the age of the solar system. Now, it's the oldest aroma on Earth, much older than the Earth's surface by about 500 million years. And I'm smelling it. It's got a kind of a old cigar butt smell or dirty sock smell.
The smell gave Professor Deemer a clue that the liquid he had extracted from the meteorite was packed with organic chemicals. When he took this extract and put it under the microscope, he saw something extraordinary.
We see beautiful little glowing vesicles that look just about the right size for a bacterial cell or larger cells.
The extract from the meteorite contained molecules that were able to form tiny bubbles or vesicles. These vesicles looked just like the outer membrane of a small microbe.
Some of the compounds were able to form membranous structures, beautiful little cell-like compartments. And we've proposed then that this would be a way for the first cell membranes to have come about on the early Earth from these sorts of molecules.
Perhaps these compounds, delivered from space, were the first steps on the road to life. But in order to form membranes, these molecules needed to have been in fresh water at just the right concentration. One idea of how this could happen is that they fell near a geyser in a warm volcanic pool. As the water droplets evaporate, the molecules start to become more concentrated and form tiny vesicles. Perhaps these self-assembling cell membranes, delivered from space, were the first steps on the road to life. The transformation of non-living chemicals into the first living cell.
So I don't have any trouble imagining that this would be a common process, and this formation of compartments would have been the first step towards cellular life.
But a simple bubble-like membrane is still a long way from being alive. Scientists still have to figure out how all the complex components that make up a cell came together to create the Big Birth. This time, the answer came from a lost world that had lain undiscovered for nearly 4 billion years. In 1977, a team from the Woods Hole Oceanographic Institution were looking for signs of volcanic activity on the sea floor, 8,000 feet under the surface of the ocean. Alongside these hydrothermal vents, they also found an incredible undersea world. Cut off from the light of the sun, it was thriving with species of plants and animals that had never been seen before. Until that moment, many scientists thought that all living ecosystems depended on photosynthesis, but here was a unique environment completely cut off from sunlight. This strange underwater world captivated Carnegie Institute researcher Dr. Robert Hazen.
And imagine how exciting it was to descend in the submarine into the black depths of the ocean where people thought there was nothing. And they find these hydrothermal vents, these places where volcanic fluids are pouring out of the ocean floor. And not only that, because of all that energy, chemical energy, heat, there's living things, there's ecosystems, life abounds, microbes and tube worms and clams and all sorts of strange crabs and other things.
After searching at these crushing depths, they found unexpected chimney-type stacks emitting plumes of scalding hot water. He had a hunch that these hot vents could be producing some interesting chemistry. Perhaps they could have produced the organic building blocks of life. He set up an experiment to find out.
It's easy to do these experiments. You see, you just take a little bit of mineral, a little bit of chemicals, you put them in a gold tube and seal it up. You put that tube at high temperature and high pressure just for a few hours. Open it up. There's all this stuff inside.
And the stuff he found turned out to be far more exciting than he'd ever imagined.
When we did these experiments, we thought we'd find nothing really very interesting, just a few simple molecules that we could analyze and maybe write a little paper on. We were wrong. This stuff had the strongest aromatic smell. At lower temperature, it was like molasses. And at a little bit higher temperature, 350 degrees or so, it smelled exactly like Jack Daniel's whiskey. People would come by the lab and say, "Boy, you guys must be having fun. What are you doing?" And we were making the stuff of life.
This strange aroma gave Hazen the clue that he too had created organic molecules. Once again, these molecules assembled into tiny membrane-like vesicles. They were behaving much like the molecules extracted from the Murchison meteorite. So Hazen had discovered that it might be possible to create these cell-like membranes close to the deep-sea vents. But other researchers believe that this strange underwater world was capable of providing more than just a cell membrane. They believe that these warm vents were where all life's component parts came together. They claim the Big Birth happened here, at the bottom of a primordial ocean. In order for the Big Birth to occur, scientists believe that certain essential elements had to work together. For example, life needed a container, which came in the form of a membrane. It needed some way to reproduce. Today, this process is achieved through an extraordinary chain of organic molecules, DNA. Life also needed an engine, a chemical process called metabolism that converts fuel into usable energy. According to Dr. Michael Russell at NASA's Jet Propulsion Laboratory, it's metabolism that came first.
Life has a job to do, basically. And I could put it like this. You could have a modern car with an engine and a computer inside, but if you take the computer out, the car will still work. But if you take the engine out and just leave the computer, it won't. The computer is the kind of regulator, but the engine is what's really important. So that's why we think there has to be an engine first, and that engine is metabolism.
Today, the engine of metabolism that powers every living thing is an extremely complex chemical reaction. But intriguingly, Russell thinks we all have traces of the first and simplest metabolic reaction buried within our cells, like living fossils, that point to where life began.
We can trace the kind of chemicals in the early Earth and see them even to this day. So, for example, there are iron sulfides in our skin, for example, and that's the little bit of rock that, to our mind, reminds us where we all come from.
And according to Russell, this is where we come from. Deep sea vents made largely of iron sulfide. He believes that this and other compounds kick-started metabolism, acting as a catalyst to enable a reaction between hydrogen gas streaming out of the vents and carbon dioxide dissolved in the water. But eventually, this simple reaction evolved to become the complex chemical engine, metabolism.
And eventually, the metabolism required DNA because it did need a regulator, it did need a computer, but to start with, we just needed the engine.
At some point, the metabolic engines acquired some bodywork, a membrane. Russell's theory gives one idea of how a simple chemical reaction could have driven the creation of more and more complex organic molecules, and eventually created the first living cell and all life on the planet. There are still many gaps, but slowly the clues to the origin of life are beginning to emerge. But now a scientist claims that he might be able to put all these clues together using the latest laboratory techniques. He hopes to start life from scratch, something that hasn't happened on this planet for the past 4 billion years. Scientists are striving to answer the great question of how life began. It's a quest that has taken them to the remotest corners of the globe and deep into the inner workings of the cell. But as one group of researchers look back 4 billion years to the Big Birth, another group of scientists is looking to the future. Around 4 billion years after nature first created life, scientists are now able to redesign it. The key to this extraordinary power is their understanding of one extraordinary chain of molecules: DNA. DNA is made up of 4 simple base molecules: adenine, guanine, cytosine, and thymine. The arrangement of these 4 molecules stores the information needed to create life. It's this natural technological innovation that's at the heart of all life on Earth today. And Tom Knight, a computer expert at MIT, wants to reprogram DNA to make new kinds of life.
Fundamentally, there is one technology of life right now. And that technology perhaps was invented, billions of years ago. And all we are doing is changing little bits and pieces of that technology.
For thousands of years, mankind has harnessed nature, rearing livestock, and growing crops. Selective breeding has improved yields and created higher quality. But now bioengineers want to take a step further. Instead of just improving nature's original designs, some want to re-engineer life, creating so-called Life 2.0.
We can now think about growing things which are not food. We could think about growing things like nanotechnology level substrates for electronic circuits. I have a student who's looking at placing atoms precisely in patterned arrays on silicon surfaces.
As well as hoping to create new forms of life, bioengineering is now giving science a chance to explain the mystery of the Big Birth. Instead of having to attack the problem from the bottom up using basic chemistry, or from the top down by unraveling evolution, scientists can now use the technology of bioengineering to try and put the building blocks of life together themselves and create a living cell. Jack Szostak at the Harvard Medical School is a leader in the field.
We're making the assumption that, okay, someday people will figure out how you make the building blocks you need. What happens if you have the building blocks? How do you put them together? How do you organize them so that they start acting like a cell?
Szostak and his team at the Harvard Medical School have set themselves the task of building a living system in the lab.
Well, we'd like to understand that transition from the chemistry of making molecules to the way that these molecules work together to give us life. So we would like to build a simple living system as a way of trying to understand that transition.
Scientists believe life evolved over millions of years. Szostak is hoping to use the latest bioengineering techniques to do it in considerably less time.
We want to make things go fast as possible. So we're making the building blocks ourselves and putting them together in just the right environment. We would like to get everything going in the time scale of a few years, which is speeding things up by a factor of, say, 100 million.
Szostak hopes to create a working cell from simple building blocks. The only way he can do this is by boiling down a cell to its simplest possible components.
One of the things that's made the origin of life very hard to think about for decades is the fact that all of the life we're used to seeing every day is so complicated.
A big challenge is to create a simpler version of the complex DNA molecule. Szostak believes the answer is RNA. RNA is also made of 4 base molecules, but instead of being wound into a double helix, RNA has only 1 strand.
Now, if you go back to thinking about really early simple cells, you could store some information in just RNA. You don't need to have DNA.
Szostak's goal is to create a simple self-replicating RNA molecule. This, in theory, would eventually form a simple cell capable of duplicating itself. If successful, he may be able to start a process of evolution.
We're interested in the beginnings of life, the transition from chemistry to the beginnings of biological behavior. And to me, the important thing that we have to think of in that transition is the beginning of evolution.
And once evolution can begin, more and more complex cells will be created by the process of natural selection. Eventually, Szostak hopes to be able to evolve a simple, self-supporting, self-replicating biological system. Some might call it life. Szostak's work might one day connect the dots between the building blocks of life and the last common ancestor, and show how inert chemicals can combine to create life. If he succeeds, it will be the crowning moment of over a century of research by some of science's greatest minds. Finally, we might solve the great riddle of how life began on our planet.